All right, here we are. It was on my to-do list to finish grades and get those back to you guys today. I wasn't feeling the best, so I didn't get to those today, but I promised to have those to you by Wednesday. The next thing is I did want to check in and see, are there any questions so far on assignment 2? The due date for that would be Wednesday, end of the night Wednesday, so after class would be fine. All feeling good on assignment 2? Or if you have questions, please let me know.
My question was on I was trying to do the histogram.
Yeah.
With the sales price. And then you asked about what's my data. And I think I just don't know how to do it, because I don't think I do. Like, I thought I did, but prior to that, I did a train data. Can you help me just?
Yeah, let's jump in there. And this is assignment 2. Yeah. This is on
be visualize target variable
histogram. Okay. I have to read in the data set real quick. So this is.
It was under the Boston housing data. It was part 2.
What did I call that? I called it.
No, it was the same one. It's just the same. Oh, you mean the thing? It's housing.
I'm going to put this in a weird place. Don't put yours here. I just haven't done all that stuff up above, so mine's going to be here. df equals. Okay, so assume you've done train test split, but for now I'm just going to do it on the df. I think what you want to do here is, let's see what our df.columns. So you want to run it on sale price here. Mm-hmm. Oops. I think you can make something as simple as that. So you can run df, try that on your data set. Your data set might be called X, or it might be called X train. So it might be X, or I think in yours it was called train. So try train, and then square brackets allow you to select a column name. And then to that, you will pass the name of the column that you want to select. And then you can run .hist on that.
So I was using SNS because of the Seaborn.
Oh, yeah, yes.
You had used that in our previous.
Yes, we can do that too.
Can you just give me another,
Yep.
Not delete that. Add another.
Let's do Seaborn histogram. Seaborn's actually better. So honestly, if you're going to build a plot, and if you use Seaborn, it's going to look a lot better than just using the pandas.
Yeah.
I see what you're saying here. Let's do that. Let's import Seaborn as SNS. And then we're going to call sns.histplot, and our data, in my case, the data was df, but whatever the name of your data is, df. And then the x variable, let's try sale price. Should give us.
Yeah. Okay.
Oh, Breakout PLT.
See that's all?
Yeah.
No, I didn't know the title was an attribute. I don't know what the title attribute is.
Oh, maybe I just need to put it in.
Yeah.
Not important. So was that able to work for you?
No. So my name is Train.
That's fine.
Okay.
That's fine.
Okay.
Train is fine. pd.readcsv, train.csv, that's fine. Can you do add one cell above that?
This one?
Okay. Right below that.
Mhm.
Yeah, perfect. And do train, and then open square bracket, and then in there put sale price. Try sale price, yeah. SALE price without the S.
Oh.
Try that. that give
Well,
you
maybe
a
because
grade
this
back.
one still has.
Yeah, so take the S out of that one. Now I know I was validating that worked, and now
Oh, it does.
there we are.
That was.
That's tricky. That's tricky. I'd like to say that never happens to me, but that just would not be true. All the time,
See, I had it
constantly.
right, you just had an extra lip.
But I did have plot.show. I had it like,
Oh,
that
that's,
was,
that's the question I have, because that keeps confusing me. When do we write, I guess, show? 'Cause
That's a
on some we
good-
write print, and then on some we write show, and then on some we don't put anything.
That's such a good question. You know what? Let me dig into it a little bit. It used to be, I think there have been some updates to Jupyter Notebooks, I think is what you guys are experiencing. It used to be you had to do this really old syntax that would be like, you might even see this if you're on the internet, it would be like mat, plot, lib, inline, true, or something like that. I can't remember. But if you ever see that and then somebody has all their code below that, that's like an old thing we used to have to put in this to make the notebooks render these. Sometimes, as you saw, like this one, I didn't have to say plot, and this one I didn't have to say plot. So sometimes that's not the case. PLT, when you see PLT, that's usually part of matplotlib. So in this case, we're using Seaborn, but I have to, let me take that as a follow-up on that. It's an excellent question. When do you need to use, plot.show, and when does it just render by itself?
Yes, because that's where I get stuck at sometimes. I will, so I'm like, it's saying it's not reading it. How do I figure it out? I don't know.
Good question. Other questions on assignment 2 so far? All great stuff. Okay, if you think of any, feel free to just bring them up as we go. We can talk about them. A quick touch base on kind of where we're at here, because we are getting closer to the end of the course. So we're sort of right here firmly at the midpoint of the course. I guess after today, we're more than halfway done, which is very, very exciting. And today is really the meat of how you build a model in the general sense of the word. And then the rest of the class, we're just going to focus on algorithms to the extent that we have time. So we're going to talk about trees. When you come to assignment 3, you'll see that I'll actually have you build a decision tree from scratch. So that will maybe the most challenging assignment, but I think it's important because when you go into interviews, that is the most common question that you're going to get. And I ask it all the time is pick a machine learning algorithm, an algorithm of your choice, and walk me through the steps. So knowing conceptually all the steps that it takes is really helpful. So we talked about KNN, that's one you could use. We talked about linear regression, though if you mess up some of the formulas in that, that can really trip you up. But I think decision trees and random forests are one that you can really explain, are very explainable, and don't have a lot of mathematical formulas to them because there's something called non-parametric, which means they don't have all those summations and all that stuff. So I think it's a really good one. So anyways, that's where we're going to get. And then we'll try to touch on unsupervised learning and deep learning and maybe just a little bit of NLP, but we won't go deep in this at all. So none of this will be I won't test you necessarily on that material. And so everything for the test will just be 1 through 6 here. Then at the end of the course, we'll have our course exam and then just our model challenge, and maybe we'll touch on a few other topics of the industry, such as ethics of modeling and bias and that type of stuff. So the model challenge, I'm just going to tell you now, though you won't need to know, the data set you're going to use for that is this Kaggle data set. What I'm going to have you do is you're going to pickle a model object. So you're going to train a model just the way that we did today. And this is a fraud data set, by the way. So I purposely tried to pick a data set that has something in it called class imbalance to just give you a little bit of exposure to some of the techniques that we're going to give you a chance to apply some of the techniques that we're going to talk about today to this data set. There's no threshold that you have to perform for this. Just if you have a trained model that makes a prediction on this data set, that's fine. So not looking for anything, not looking for you to have like a score above XYZ. So you technically could just not use any of these methodologies and still do fine. So didn't want to put too much pressure on for that piece at the end. It's just about learning how to train a model, start to end, pickle an object. So should be very achievable there. More to come for that next week. So just stay focused on assignment 2 here, but just wanted to give you a sight there. All right, so modeling methodology. We're going to go through 3 different sections today. I think this first section is actually going to be quite long. So as you see, I think this will take the whole first hour. So I have the break here built like halfway through this section. So we're going to talk about generalizability, incredibly important concept, very foundational to all machine learning. That is the entire reason we build machine learning models, is to generalize to the real world. So when you have new data that you don't know the answer to, you can ask the question, is there a cat in this picture? I truly don't know. Can you answer this for me? And so that's the whole point of model generalizability and the whole point of machine learning. And then for the second part of today, or the second section of today, we're going to do grid searches and cross-validation. So this is probably actually all stuff that you guys have already seen in the code, because it's been here and there. But now we're actually going to understand what it means and how it works. And then at the very end, we'll just brief review on feature engineering, and then we're going to talk about feature selection. So if you have a ton of features, you're probably not going to need them all, and they're probably actually hurting your model performance as opposed to assisting at that point due to cursive dimensionality. And so how do you select features in maybe a programmatic or logical way? And then we should touch on precision, recall, confusion matrix. We won't go in depth into these because there's a whole course on like machine learning metrics that you guys are going to do next. And so I won't ask you to like calculate any of these, but I think they're helpful to know, and they'll lay some good foundational knowledge. That way, as you're building your models, such as this fraud classification model, you can kind of have an idea of which of these metrics would make sense for that. Okay. And then if you guys want, we can skip the breakouts today. If you want to get out earlier, we can do those. I'll leave that up to you as we get to them. All right, let's move along here. So I think I shared a link to each of these notebooks. You should be able to find them. When you run them right now, they will not show any of these images because I haven't moved those to a location that is accessible to that Git repository. So I will do that, but it may not be till like this weekend, for example. So I have all the images, I just have to organize them. So the modeling methodology, when we talk about modeling methodology, and this is the term that I use for it. I tried to search this on the internet and didn't have like a lot of great results come up. So if you guys happen to find something better, let me know. But when I think of modeling methodology, these are the steps, the order of steps that you take to build a model. And they're important because sometimes if people put them out of order, they can inhibit things like generalizability. So we're going to talk about all these things today. So what is a machine learning model? We've been talking about this kind of through this whole class, but the whole point is to train a program that can make decisions on previously unseen data. So that's a term that you're going to hear over and over and over again. Previously, or unseen data, or how does your model generalize to unseen data? So a couple of examples in here. In NLP, natural language processing, which is processing of textual information, machine learning models can parse and correctly recognize the intent behind previously unheard sentences. So we'll train you on this data over here, and now I'll give you a new sentence that you've never seen before, and tell me the intent on that sentence based on the patterns that you detected from this previous training set. In image recognition, machine learning model can be taught to recognize objects such as cars or dogs, and it can perform tasks having been trained with a large data set. So when we talk about the training of the model, that's really what we mean. And during training, the whole point of training, why do we train a model? It's actually for optimization. So we're optimizing the algorithm to find certain patterns or outputs within the data set. So think about our linear regression. You've got your X and your Y axis. We're optimizing to try to move that line closer to the best fit of the data. So maybe, the data was sparsely located and then it was way down here. Well, we're optimizing to have that parameter be the best fit to that data, have the lowest error, the lowest loss. And so the output of this process is called machine learning. And I've got source links here to all of this, any text blob I have in here, kind of where I got that from. So and there's more on these links beyond just this blurb of text here. So they're kind of useful if you're interested. So when we think about modeling methodology, and I'll break it down a couple different ways. I'll get more into the weeds at the end of this, but I think of it as these 7 high-level steps, and each step has a lot of kind of components in it. But first, you need to contextualize the machine learning problem and the class of the domain. What is the problem that you are trying to solve? What are you trying to do? And then class of the domain, well, what type of model would fit that? Is it a classification algorithm? Is it a regression algorithm? Is it reinforcement learning? So we're not going to talk about that today. I think more in the next course that may be more helpful in that. And then identify and prepare the training set. So this is everything that you guys have done in kind of an EDA class or a data analysis class. So how do you find the data, write your SQL, get everything together, and prepare your training set? What we're going to talk about today are these 2 pieces in bold. We're going to split the data set into training and evaluation sets. So you may have already seen this, but we're going to dive more into what is train test split, or what I like to actually call train validation test split, and I'll talk about why. And then you would explore different algorithms and prepare and clean your data set, and then finally perform machine learning optimization. So we're going to talk about the optimization, the model methodology part of the optimization, and then this whole component of deploy the model, which is more than just put a model and feed it data, because now you have to restructure your data to be representative of what you're trying to predict. So if I created a data set and I said, give me all the people in the past who have committed fraud or haven't committed fraud, well, in my new data set, when I deploy it to production, I need people I haven't yet made a prediction on. So I need all the people that you don't know have committed fraud. So it's a different type of representation of the data, but we won't get into that.
How do you do that when your data is limited?
What do you
for
mean?
example, maybe you put, so it says train with a large data set. So when I think large data set, you mean you have thousands and thousands of, data, cells of data, whatever. And then you train that, and then is the data, the unseen data then have to be that same amount of large data set?
Oh, good question.
Or could you do with a smaller sample and then could still be true, sampling? I don't know.
Yeah, no, that's an excellent question. When we make predictions, it doesn't have to be, if we train a model on 500,000 rows, when we make predictions, it doesn't have to be on 500,000 rows. If we've done our methodology correct, so that's the whole point of today, if we've done all of this correct, it should generalize to even just a sample of 1 or a sample of 2. We've vetted it and we've kind of rubber stamped it and said, we checked all our boxes and dotted all our I's, crossed all our T's, and made sure that this generalizes to the sample set that I'm applying it on. So it shouldn't matter. I will say for your training set, if you're working with less than 100 rows of data, 100 observations of data, there's probably different techniques you should apply. So I am making a big assumption trained with a large data set because that allows us to use some of these foundational assumptions called the law of large numbers. So if you actually go look at linear regression, and maybe a lot of you notice this, there's actually assumptions with linear regression that your data has to have this certain shape and homostaticity and a whole bunch of them. And I think I shared them in one of the documents. I didn't go into those because once your data gets big enough, you can kind of ignore those assumptions and you can say, I'm going to rely on the this basically theory that the law of large numbers, that things will converge over time because I have so much data. But that's not true if you have less than 100 row. That's their like thumb in the air. I mean, if you have 101, not necessarily true. But if you have about 100 rows of data or less, you actually should use those modeling assumptions. And so I would push you back towards statistics as opposed to machine learning. So I'd say develop a hypothesis. I hypothesize that, this is going to have that impact, and like go through that formal looking for p-values and kind of that formal statistical methodology. Did that help?
Yeah.
Okay. That's going to be better, I guess. The model may not work well in that situation. So small. So the term generalizability. So when we talk about model generalizability, it refers to the model's ability to adapt and react to this new data, this unseen data. But we're making an assumption here, which that it is drawn from the same distribution as the one that's used to make the model. So that's what that's saying is basically, you guys familiar with the MNIST like data set? There's the MNIST fashion data set, MNIST number data set. There's two of them. So if we trained our model on this data set, this is like a standardized data set. Clearly somebody has put in a lot of time to like center these images and make them all black and white. And we trained a model on this, and then we tried to use the model to predict, was it a shoe? That's what we're trying to do in this, is you're trying to say, is this a shirt or is this a shoe? If we use this, trained a model on this data set, this was our training set, and we tried to use this to predict on Google Images, given a Google image, can you detect whether this is a shoe or a shirt? It would not perform well. Our model would not generalize because they're not being drawn from the same distribution. Those are not the same data sets. So when you're training your model, it's very important that you build it in such a way, you collect your training set in such a way that it's the same distribution as the one that you're trying to predict on. So with this, used to have middle schoolers come in, I'd teach them about data science for a work thing. And I would build a model that would predict their musical preference off of a data set. And they would come up and they'd type in all their features, and then the model would do horribly wrong. And then we'd go and we'd look at how that model was created. And it turns out it was just a collection of high school students in the Netherlands. And so I'd ask them, why do you think this model is doing poorly for you, high school students in the Netherlands in 2015 or something like that, right? And so that's generalizability. That gets to this point of same distribution. There are different distributions of people, right? Those are not the same distributions, not the same points in time. So when you build your model, you're going to want to make sure, or when you build your data set, you're going to make sure what you're predicting on is the same distribution as the model. Okay, beat that with to no end. Continuing on.
It's interesting that you show that with the clothing, because we're actually using those for drones in search and rescue.
Really?
So you could, we have a drone for part of our team, and what we do is we'll deploy it, and through machine learning, they're trying to take different images and then run it through this to see if what we believe is the area of interest is truly.
Sorry, I think I added someone to the stage that wasn't muted. 1 second. Charity, how do I mute you? Have it muted. I got it. Sorry about that. Please continue.
No, it's interesting you show this. So I was wondering, what is this data set that you have so that I could see what they're using?
Oh, sure. So this is the MNIST data set. It's a very well-renowned data set. And I believe this actually stands for, don't know what the M stands for, National Institute of Science and Technology, maybe, but it's an organization, or it was an organization that's basically responsible for propagating more knowledge in the world. So this is the second data set. This first one, it was a digits data set. I mean, you can see it in lots of different places. It's most commonly applied with TensorFlow. So TensorFlow is a neural network package, and it's this curated data set of all these digits. And what they did with this data is they centered all of these based on center of mass, and then you can see there's kind of like these grayscale images. So they did a lot of things to curate this data set to make it much easier to interact with. So a little more friendly for models, so that we can make some assumptions about this data and kind of prove that different theories or models work better or worse for different things. So usually in like science and math, you try to simplify your assumptions and prove it on a really simple case first. And so this was this first case. So this digits one was actually curated for the post office, I believe. The post office wanted to be able to read handwritten letters and then automatically sort those with a machine. So this was the problem that was formed the generation of this. And so MNIST made, another data set, and this is the fashion data set that they made for that problem. I'm not as familiar with the exact background on here. So yep, original was handwritten data sets, and then, like I said, this is basically like a benchmark to kind of validate how different algorithms improve upon each other. Everybody's very familiar with their data set. So if somebody comes up with a totally new neural net, when convolutional neural nets came out, then it performs this much better on this kind of standardized data set. I don't know if I answered your question.
Yeah, I pulled up the site, and so thank you. That's
Perfect.
awesome.
Okay, wonderful. Yeah, very, very foundational to the field of neural nets. We'll touch on it in this course, but there's a lot to neural nets, so we won't have time to go into it. But if you guys are interested, happy to always chat more about them. They're very interesting. So in generalizability, let me see where. So there's one thing that we'll talk about, which is overfitting. So if your model is too well on the data set, and we'll talk about this a little later, that makes it kind of incapable or poor at generalizing. And it makes erroneous predictions given new data. So you'll train it on your training set, and it'll say, I do really, really well. And then you'll give it new data that does very poorly. That probably means that it's not generalizing well. So that makes the model ineffective and not very good at predicting on unseen data. So what do we do? So if we want to make a model able to generalize, there's two things that you can do. One is you can use a resampling method to estimate the accuracy of the model. That's train test split. This is the train test split method that we're going to go through. Oh, sorry about that. I like to double click on things. And the second one is the resampling method is the cross-validation we're going to go through. And then the other one is holding back a validation data set. So that's train test split. So here's a very simple picture that just says, hey, is this sample representative? It either is or it isn't. I don't know how useful that is, but this one's perhaps maybe slightly more useful. By the way, sometimes people refer to this as memorization versus generalization, because people like things that rhyme. So when we talk about predictive generalization, we have our training data in as XY, and we have our test data here as XY. And in this case, the test data are these red dots, where X is, at this point on the number line, so maybe like a negative 4.3 or something. And our Y output for that is at this point on the number line, so maybe like negative 12 or something. And so that's what this point represents. This is a new point. So the model was trained on these little black dots here. And this blue line would be overfitting. This is memorization of the exact pattern that creates the training set. So this function is very extreme. So you can see if we put in this point of negative 4.3, the function would actually predict way up here in positive 12, which is of course not the case for this. And it would have a lot of error because the distance between this point and this dot is very great. And so you can see that these red points, these new points in the data, don't generalize. This blue line doesn't generalize. This black line is very, very simple, but maps the data. So this is what we've been doing, the linear regression. It's just a straight line. It is very simple and maybe even underfit, but it does generalize a little better to this unseen data because the errors are going to be smaller. The distance from this black line to this red dot are going to be smaller. Okay, so let's talk about train validation test split, which is what I'm going to refer to it as. You'll see it mostly on the internet called train test split, but I think, and that's probably because the package is called train test split that we're going to use, but I think train validation test is the right methodology here. So I'm going to be a little strict on this part of the methodology because I think it's important. So the train test split, it's a technique for evaluating the performance of your machine learning model. So we can train on all this data, but unless we set a test set or a validation set aside, we don't actually know how it's going to do on the unseen data. So this setting aside a test set or a validation set allows us to go into this like pretend mode. And we say, oh, let's pretend like we never actually knew this data. It didn't exist. We're going to put it under lock and key. And then when we're done with all our experimentation, then we're going to release it and see how well we did. So it can be used for any of the problems, classification or regression, any of these supervised learning problems. You could probably use it for some unsupervised tasks as well. But so this involves taking this data and dividing it into two subtasks, where the first one is we're just asking the model to learn the task. So we're asking it to learn that function. We're asking it to train the parameters that best fit that data, to learn how to make predictions on that data. And then in our validation set, this set, I'm going to say that you're allowed to use more than once. So you can, let's say we have a training set and we train a random forest and a gradient boosted tree, and we train, all these different types of models. Well, you need some way of comparing model 1 to model 2 to model 3 to, a neural network. And that's what the validation set does. So the validation set enables you to select, is this the best model of all these competitors? You got to be careful. Don't overuse the validation set. Otherwise, you're going to run into the exact same problem that you would if you just use the whole training set. You'll be overfit to the validation set, and then your model won't generalize. But generally, people use it to select what is the best model. Okay, they're called model challengers sometimes. So we put a bunch of challengers up there, and that's what we're going to do with your models at the end of the course. You're going to give me all your models. We'll put them all against each other in a validation set just for fun, and we'll see which one we would select as the best, and then we'll compare it on the test set. And so the test set is designed to be used exactly once, and that is the moment before you deploy a model to production. That is that's my preference, I guess. That's my argument. You may see other things in practice, and especially in these notebooks like this, if I'm just doing a train test split to describe a concept, you may not see that here. And that's why a lot of times this gets misused or misrepresented, because people need ways of explaining concepts succinctly, so they'll do a quick train test split. But then when people go and apply that in practice, they'll be using this test set more than once. And the idea is, no matter if you're training your data for days or weeks or even months, you have this test set that's just setting to the side. And then the moment you're ready to deploy it to production, it's actually interesting. I should highlight this in here. I forgot to mention this. What you'll do is you'll actually train over everything, your whole training set, and use that model to validate multiple times. And then when you're ready to deploy to production and we've got a perfect model, what you do is you actually combine your validation and your test set, and you retrain your model with the same parameters that you selected. And I'm realizing I should have made a visual to show this. And then you evaluate on your test set, and that is your only assumption of how well your model will do on unseen data. And then you take that little performance metric and you set that to the side, and you're like, okay, my model has 0.8 for accuracy. Accuracy on 80% of the data. I assume that's how well it's going to do in the real world. And then you actually take all of this data, your training, your validation, and your test set, and you add it back all together and you retrain your model. So in effect, it's actually a different model because it has more data. You give it all the data it can possibly have before deploying to production. So you retrain it across all of these data sets, but you don't re-estimate it. Your estimate for how that's going to perform is how that model performed on the test set when it was just the training and validation. So it's a bit of an odd thing there, but that is the methodology. Okay. And keep in mind the size of your data set here. I'm going to be doing 60-20-20, so 60% training, 20% validation, 20% test. But check out your data set, and if that size doesn't make sense, then make validation and test smaller. Or maybe you're one of those cases where you can't have a validation set and you just have a test set, and that's okay too. You don't want to slice your data so small that it's not helpful in training. Okay, so I guess this was another thing that's important. There is model time at training, and then there's something called inference. So inference is when we're making the prediction, and you'll hear that term a lot, inference time and training time. So we talked about how you have this data coming in, your training data in the original state, we're going to clean it, and we're going to select certain features, and then we're going to have a training set of data, and that's what we're going to use to build our machine learning model. At time of inference, you have to go through these same steps. So you can't just take your new never seen data and go straight to the machine learning model. If I took a column and it was from an Excel sheet and it was supposed to be an integer, but my program read it in as a string, you're going to have to convert those strings to integers in the inference step as well. So whatever data prep pieces that you do when you're training your model, keep in mind that you have to do those here as well. And that's why that pipeline thing that I showed you is so powerful, because it keeps the integrity of those steps intact. So you don't miss something when you're copy pasting to your production deployment. So once we have this selected data, you have your test data here and your evaluation. So you have your validation set here. Okay, I think that's the only point I wanted to emphasize, just same steps for cleaning and feature selection. So if you select 3 features to put in your training set for your model, you have to only pass those 3 features to inference. You can't pass all 10 columns. Your model will be very confused. So this is the sklearn train test split package that I'm sure you guys may be familiar with by now. So we're just going to dive into this a little more. We're going to make some fake data here, and then we're going to split this data into train and test. And for me, I made this fake data, and then I'm gonna make this thing called dataset. I'm gonna make it a data frame because it was an array before, and I'm just gonna make a copy of the X data. And then I'm gonna add a new column called Y. So I'm squishing my X and Y data together into one data set because I wanna show a functionality of train test split. So you can use train test split this way. If you have one data set that has your X and Y all in one, then you can call train test split and just pass your whole data set, and then say what size, test size here, and then we're passing a random state. I'll explain what that is in a moment. So you can just do that, and you get a training set and a test set, and it has all your X's and Y's squished together. So here's my training set. It's got my feature 0, my feature 1, and then my Y in it. And here's my test set. It has feature 0, feature 1, and Y. So note here that a random seed, or in this case, a random state, means that we will end up with the same exact samples every single time we run this. So into the training set, we will always have sample 2, 0, and 3. And into the test set, we'll always have sample 1 and 4. If you want to change things up and see different behavior, simply take the random state out of here, rerun this a couple times, and you'll see that that will change that. But the reason people put random states in is because it ensures something called reproducibility. That means another experimenter could come in, run the experiment, and produce the exact same results, like down to, you know, the decimal point of the performance that you got on your model. If you don't have random state, it's okay. It just means that if you have a data set that's, you know, thousands and thousands, and you shuffle it differently than somebody else, they have a different separation between test and train and validation, they could get different model parameters or different model results. They said, oh, I trained this and I ran the exact same notebook and I got an accuracy of 0.8. How'd you get 0.92? That would probably mean your data set's really volatile and something else is going on, but it is possible if you don't have random states. So people sometimes like to put that in there to just ensure that integrity. Yeah.
So let's say your data has 500 rows. How do I, like 42, where does 42 come from? Or like,
oh, that's an excellent question. You can put anything there. So
you put 1,000.
Yep.
Even though you only have.
It is interesting. That's not what I expected to happen. Oh, because that's different data set. There we are. 1 second. I think I changed something in here. Yeah, okay, good. That I got very confused for a moment. So it doesn't matter, you put 1,000. So you see when I put a different random state in there, notice that I'll get different numbers though. So it's just a way of selecting, it's way of choosing how to be random. So it's not really being random, it's actually very deterministic in terms of how it chooses to be random.
So not like every 1,000 or every, that's what you mean by random state, right? Like every point, or I don't know, say.
It's, so let me think of how to
Every
describe
1,000, I guess that's what I'm trying to figure out, like, or is it every?
It's any number you want. So I can put 1, 2, 3 in here and it'll be 1, 2, 3. It'll be a different way of choosing randomness there. But the way that it chooses to shuffle things randomly is going to be exactly the same. So
it doesn't matter if you have 1 digit or multiple digits?
No.
So what's the point of doing more than 1 digit then at that point?
So sometimes when people are training models like neural networks, for example, it really matters. Randomness really matters because when you're trying to initialize, really important part of neural networks is initializing your starting point. So you have these gradients, which picture somewhere, maybe in a different notebook. You have these gradients, and you're trying to. Here we go. I knew I had it somewhere. So you have these gradients, these parameters, which ignore that for a second. Just understand that you're a ball, and you want to roll down a hill, and your goal is to get to the bottom here. And so it really matters where you start. If you start here, it may be really hard for you to get over here. Or if you start here, you may just end up here. This is something called a local minima. We don't have to talk about that. But my whole point here is randomness really matters because it changes your starting point. So sometimes people don't want just one random state to try. They want reproducibility. Sorry, trying to figure out where we were here. There we are. They want reproducibility. They want other people to be able to run their algorithms, but they also want to try different states of randomness. So what if I initialized at every corner? What if I initialized all in the center? What if I they want to be able to try these different variations on randomness. Randomness in computers, if you guys have ever taken computer science class, is actually super, super interesting because it's actually not random at all. It's all based, it used to at least be based on like the time clock of a computer, which is really fascinating. So I'll see if I can send something out about that. So
random exists today, I guess, in its fullness. When it comes to some of these
it's
models.
pseudo-random. We hacked it to like represent what we think randomness should be in the world, but it's not truly random by the definition of like just totally random, but it works well enough for these algorithms.
The same, like, idea of like, you know how you do the penny, how many times we get to the tail, how many times we get the head, the likelihood of being more tails than heads or higher, I think.
Yeah.
So like that, kind of where, it sounds like you're manipulating, but okay.
Yeah, absolutely.
Okay.
I'll see if I can send more on that. It's a really good question, and random states are important. So another way to train, test, split the data is by passing X and Y. Instead of just passing the whole data set, we pass X and Y separately. And that's what we've been doing. When you pass it that way, notice up above here, I only had to expect two outputs, a training set and a test set. When you pass X and Y separately, it assumes that it's because you want to work with them separately. And so it's going to, now it's 4 data sets because now you have X train, Y train, X test, Y test, instead of just train test. It assumes you want them split by X and Y, just like you passed it in. Again, we have our random state here. And so you can see our shapes here of our data sets. We are getting 33% in our test set, and then the remainder in our training set. Oftentimes, that's useful, and you'll see this most of the time. And this is why it's called train, test, split, because that's what the class is called. It's literally called train, test, split. However, most of the time, we're probably going to want a validation set, especially if you have a sufficiently large enough data set. I would encourage you to do a validation set if your data allows. And so you're going to want to do this. You're going to have to run this function twice. I imagine in the future, I will bet anybody $100 that in the future they'll have a train validation split data set. sklearn's very, very good about adapting their code when it's functions aren't making a lot of sense or a lot of redundancy in the way that something is being handled. And there is redundancy in this. So you have to do something a little funky here, which I imagine will be fixed in the future. But train, test, split, you pass it your X and Y just before, and then we're going to say our test size is 20%. And I created a data set here called X train validate and Y train validate, and then we have our regular X test, Y test. 20% will go to this X test, but the other 80% will go to this train validate Y and X. And then we're going to pass that. We're not actually going to use that anywhere except here, where we're going to pass that train validate, X train validate, Y train validate. And now we have to say our test size is 0.25. I'll explain that here in a second. And then we have our last couple of data sets here. So we've got our train validate, X and Y sets. So notice I wanted a 60-20-20 split, but I had to say test size is 20% here, and then I actually said it was 25% here. And that's because this X validate is only 80% of the data. So be careful about the test size parameter to the second split function. For example, you would need to pass 0.2 and then 0.25 because 20% of the entire data set is 25% of 80% of the data set. That's like it's like a little tongue twister there. But if we wanted 20% of all data, so I broke it down here. If we had 10 records and we want 2 in the test set, 2 in the validation set, and 6 in the training. In the first train test split, we would put 2 in the test set and 8 in the train validate data set. In the second train test split, we would put 2 in the validate and 6 in the, 6 in the training with a sampling of 0.25. And that's because 2 divided by 8 is 0.25. 2 is 25% of 8. So it's 25% of this data set, but it's, all right, you get it. It's 20% of the whole. And you can validate that by running shape on these, and you can see that these 2 data sets are the same shape. So our validate and our test are the same shape, which is what I was going for. Okay, so stratification is another feature. I'm sorry, I better not use the word feature. It means something very specific in data science. Stratification is another parameter, another argument that you can pass to train test split. So you can pass this thing called stratify. So that's what we're going to talk about. Some classifications problems, and in this text from this this blurb framed it in terms of the y variable that you're trying to predict, your y hat. But it doesn't have to be your y hat. It can be a column. Okay, I'm going to come back to that. So some classification problems do not have balanced examples for each class. So think about fraud. Fraud, 99% of the people do not commit fraud, but 1% of the people do. So it's something called class imbalance. That's a heavy imbalance data set. And if we just apply randomness to that, to our sampling, what's going to happen is by random chance, we might not get any fraud examples in our training data set because 99% are not fraud. And so we would need to use something to force the representation of our target variables into our training set. And so when you use stratify, it's saying, based on the column I'm looking at, I want the same distribution in my training and test set than what is in my overall set. So if I have 99% to 1 in my overall data set, my training set will be 99% to 1 of that label. My validation set will be 99% to 1 of that label. My test set will be 99% to 1. And so you are forcing it to have equal representation of some column. Now, most of the time this is used for target variables. Like I said, you can actually use this for columns too, feature columns too. So occasionally I've had situations where I've had to force it to represent a certain feature that was really important but very imbalanced. And so this is no stratification, so that's what we did before. And then this is stratification, and I ran these so that you could, you can compare the difference between the two. You can see that this one is very not equally represented, and then this one's very equally represented here. Okay, so that's just a little side note there. It's important, I don't have an example here, but it's important that when you are building a model, it makes a lot of sense most of the time when we look into the real world. So in this class, we're trying out some data sets and stuff, and we're just going straight to the model building process, and we're just applying an algorithm. But in the real world, you're probably going to want to set a baseline. And sometimes you can come up with like a logical baseline for a model. Usually maybe the average of the data set can be a baseline. And so you're going to want to create just like a high level baseline. That way, when you try a model, you know if it's just doing absolutely terrible. Usually kind of the rule of thumb is for this, what is a coin toss in your data set? In your data set, what represents like a 50-50? If you're doing worse than a coin toss, you probably shouldn't use a machine learning model. You should take 10 steps back and figure out what's going on. Why is that happening? So you need kind of a salient, like how much better than just choosing something at random is this? So sometimes randomness is used for a baseline. So if we're doing classification, apples, oranges, pears, if I just choose a label at random, that's a baseline. Pick either apples, oranges, or pears by random, and then tell me what the performance metric is. And by random chance, I will sometimes get things correct. And so maybe my performance metric is 16%. If I have a model that does worse than 16%, I should just use the random model, right? I should just choose a label. It means I'm doing something wrong. So here's an example for words. If we want to label things like adjectives or nouns or verbs, perhaps we can just always predict noun. This is also another common way of doing a baseline. Just always predict something. And so if we always predict apple, maybe we do 30%. Or if we always predict a noun, we had an error rate of 87%, which is bad. We want to minimize error rate. Remember, some metrics you want to maximize, some you want to minimize. Error rate, we want to minimize. We want that to be small. So maybe we look at the most common tag. So maybe we have a bunch of examples of fruit, and we see that how many times is it labeled adjective. So we can say, 19, we get a 19% error rate there. So that's a good baseline. So if we're creating a machine learning model, our machine learning model should be more sophisticated. It should be able to do better than just predicting the most common tag. Because if most common tag does better than the model, then let's just use the most common tag. So state of the art here, 2%, and it's probably even better now. It's quite good. So that kind of gives you, when you're creating your own models, maybe start with a baseline, try to think what's something random I can come up with, or what's just like an average for this that would be kind of somewhere good to start. And then use that to analyze your errors, and then build a model and see what kind of lift you get. The other thing I'll add is just iterate. Add pieces one at a time. So add data one at a time. Maybe don't try to start with this huge universe of 70 data sets all added together. If you add components one at a time, you can see how they're going to help or hurt your model. Okay, overfitting. I think, is this where I said we were going to break? No, we're going to do overfitting and then we're going to break. I told you this first section was really long. So overfitting is very related to the term generalizability, and it occurs when our model it basically memorizes the training set. So it gives really, really accurate predictions for the training data set. And so your model may have like a 99% accuracy on the training data set. But when you give it new data, it does quite poorly. And so this is the example we were looking at just a little bit earlier. And so when we train models, we want them to be generalizable. We want them to generalize to new data. And so what I'll say about this one's overfit because it's, this is something called a decision boundary. It has this decision boundary and it kind of wraps around here and does this and all this. And so it's very overfit to the training data. It gets every single classification correct. Now, that's not to say that if a model gets every single classification correct, it is overfit. That's not necessarily true, but this is just a simple representation. And then this one might be underfit. Maybe the decision boundary is actually a little curve here. Maybe that's the real decision boundary. And so perhaps it's somewhere in between these two. Okay, we'll do bias variance trade-off when we get back, which is related to overfitting. So let's take 10 minutes. All right, we're gonna fly right through today. So another concept, I would be really remiss if I didn't mention, this would not be a machine learning course without mentioning the bias variance trade-off. But it's very related to overfitting and to generalizability, so very in keeping with our topics today. It represents the balance between the model's simplicity or the bias and its sensitivity to fluctuations in the training set. So the variance, how it performs with other types of training sets, not just the one that you handed it. So striking the right balance between the bias and the variance, it minimizes the total error and achieves the best performance. So when you think about your error for your model, where it's getting things wrong, it can be broken down into these 3 different causes, and we sum them together. It's error due to bias, error due to variance, and error due to irreproducible error. And these are very conceptual things, by the way. People don't typically actually quantify things in this way, so you'll hear it as kind of like a theoretical thing, but you won't see people plotting their bias and their variance of their model, though I suppose perhaps you could find a way to do that. So this error that's not reproducible, it's this error that we assume exists in the world, and we can't model it. So in theory, there is error in everything, a tiny amount of error. And if you look at mathematical equations for like linear regression or logistic regression, you'll actually see that in mine, I didn't add this, but there's like always an error term at the end, because there's just a little bit of error that we can never really truly map, or randomness. Sometimes people refer to this as randomness. So there's that. We don't do anything with that. We just acknowledge that it's there. And then there's bias. So bias is the difference between the model's prediction and the true values. So if your model gets really, really good on your training set and predicts every single prediction correctly, it's overfit, like that picture that we said, it probably has really low bias. It does very, very well on its training set. But when it has low bias, very low bias, almost zero, it's probably going to have a high variance, meaning that the model, its variance is the measure of the model's inconsistency across data sets. So if you gave it a different data set and said, well, predict on this one instead, our validation or our test set, it would probably do poorly because it's overfit to the training set. So when you have low bias, you have high variance. Now, on the flip side, if we make a model that performs really well across all of our data sets, no matter what data we gave it, it still made predictions. So it performed very consistently. So if it performed 0.8 on our training set, it was 0.8 on our test set, and it was 0.8 on our validation set, and 0.8 on this other set. It had the same model performance. So very, very low variance, but it probably has a high bias, meaning the model's probably not performing as well as a model that's fit really tightly to that data. And so there's a trade-off. That's hence the word trade-off between bias and variance. And I have this in the notebook, but it's super tiny because I tried to pull this off the internet and that didn't work well. So we're going to look at them on their actually source websites. So there's this plot that people, which I have a simpler one in here, but I couldn't find the link to that one. So we're just going to use this one. There's this plot people sometimes use to describe this context, the difference between the bias and the variance. So the bias here is this line. We have high bias and then it gets lower. But when we have really low bias, like I said, we have really high variance, and we have high variance and then it gets lower, and you get that trade-off. So it's this little X shape, this trade-off. What we're targeting for is this white area, this area between these purple dots, where the bias and the variance are the closest to each other. I mean, if it was perfect, we'd have this spot exactly right here, but we're just targeting somewhere in between. Once we get to this side, it's probably overfit if our variance is high, and if our bias is high, it's probably underfit. That's actually the opposite of what I said. So I'll figure out what's right there. That seems backwards to me. But so anyways, so we want to try to get here in this middle area. And then there's just this error that we can't do anything about. That's just going to exist. It's consistent in life and nature and everything. And we just expect that it's there. Okay. That's fine. So that's the bias variance trade-off. If you ever hear that, now you know what that is. We won't do too much with it, but just wanted to, important term, that I should call it out. Occam's razor is one other thing, and you'll hear this. This is generally applied to everything in the world, and so you'll hear this more than just machine learning. But in machine learning, they use it to say that the simplest explanation is probably the better one or the correct one. So you've got this friend who's going on this crazy complex story and thinks that all these things are happening, and then you tell them, well, the simplest answer is probably the right one. If you think that this is because of this, that's probably what's happening, and that's what Occam's razor is. So when you're building a model, don't just go straight and add a bunch of complexity. If you can build something with a linear model, it's probably going to be a better fit for that data and a better fit for reality of trying to predict on your test set. If simpler is typically better, we do use complex models sometimes, but they're sort of necessary at that point. Okay, so decision boundaries. I just wanted to give you a visual graph of what a decision boundary might look like. So we talked about K and N, K nearest neighbors. Remember, N is the number of neighbors that we're going to look at, and we're going to classify based on the number of neighbors, what a new label would be. And so in K and N, in a two-dimensional space, if we had just had two features, X1 and X2, and we visualize a lot of things in machine learning in two features in 2 dimensions because it's easy, but obviously you can visualize this in 3 and then maybe understand that as we go to 4, it gets really complex. But here in 2 features, if we have this purple dot here, anything in this area that landed inside this purple zone would also be labeled a purple dot because we're saying K equals 1, and this is the closest neighbor within this amount of zone. And so you can see that this decision boundary isn't very smooth. Then we get to K equals 5. We're looking at the 5. So this is maybe would be an example of overfit, overfit data. It's like mapping each and every single point. And then we get to K equals 5. Look at the 5 closest neighbors. Then we get like a slightly smoother decision boundary because now you're kind of taking the average. If I look at all 5 points, where would I map it? And then we get to K equals 25. And you see we can start to get like a more representative like decision boundary. And we're going to get some things wrong, but this generalizes better to our data set. So I like to use this visual to explain that it's okay if your model's not 100%. That probably means on your training set, that probably means it's generalizing well in some cases to your test data set. It's a balance. It's a trade-off. I think there's one more thing I want to mention, and then we'll talk about. Oh, it's quite a long thing I want to mention. Sorry, I thought that was shorted. Then we'll finally get to the modeling methodology steps, which is the whole point of all this. But these are so at the topic of modeling methodology, another important concept. So these are other important machine learning concepts, and there's no other place in the course for them, so I just throw them all in here. So I apologize for the brain dump. So one last random thought here. There's something in machine learning models. We're trying to classify, 1 or 0, or apples or oranges or pears, or, we're trying to make these predictions, maybe the price of a house. However, under the hood of many of these machine learning models, as you probably already know, they're often predicting a probability. So these are actually probabilistic models. So they're not typically predicting 1 or 0. They're usually actually predicting a probability a range from 0 to 1. And it's a measure, that probability is a measure of uncertainty about the model's prediction, because it's not always very confident that it is an apple. Sometimes it thinks it's an apple, but it's not really sure. And so probability is what it uses to determine that, to represent that. And the default value, it's very important to note that the default value for normalized predicted probabilities between the range of 0 and 1, which most of ours are, is 0.5. So typically, when you're looking at binary classification, for example, is this an apple, yes or no, 0 or 1? Any probability greater than 0.5 is class 1, and any probability less than 0.5 is class 0 by default. It's just very important to know that that's what happens by default under the hood. That doesn't mean that has to be your probability in how you classify things. And in fact, in many cases, you don't want that to be the way that decisions are made. But that's just what comes by default. And then you, as the data scientist, have to change or adjust this as you see fit. So sometimes, we'll get into this, but you'll want to calibrate the probabilities. And all that means is if you have 100 predictions, you don't want all of your predictions to fall between the range of 0.1 and 0.6. You want 10% of your predictions in 0.1, 10% of your predictions in 0.2, 10 in each decile, in each 10th decile. And so that's calibration that people do sometimes for various reasons. And there's many other reasons. You can read this more, but just trying to point out that classification methods have thresholds, and either it's set by you or it's set by default by the algorithm. And these thresholds change what we predict as what our metrics will be. And so, for example, if we have this logistic regression, which I recognize we're talking about next week, but just understand that logistic regression just predicts 1 or 0, it's binary. Either sneaker or not a sneaker. So this is our image fashion data set here. We're predicting sneaker or not a sneaker. And if we put our probability threshold here, which looks like it's maybe like 0.4, we're saying everything above 0.4, we're predicting it's a sneaker. So these are all the things we predicted were a sneaker. And everything below 0.4, we're predicting is not a sneaker. So you can see that everything we predicted was not a sneaker actually was not a sneaker. So we have really, really good precision there, which we'll talk about that metric a little later. But you can see that when we predict above the classification threshold, when ones that we were predicting that are sneaker, you can see, oh, we got 1, 2, 3. 3 of them actually weren't a sneaker. So then you can compare like your confusion matrix here. You can build that, but we'll leave that out. I was just using this because I thought this visual was helpful. So you can put this anywhere. You could put it right here. You could put it right here. You know, you're going to want to choose what makes sense for you, but you can adjust the probability threshold. That's what it's usually called. So what does that actually look like? So let's make a data set here. We're going to generate some X and Y. We're going to make some fake data here. These are just some different ways of making fake data. And again, we're going to split into training and testing, and then we're just going to build a logistic regression here, which we'll talk more about next week. But we're going to make it predict on this fake data that we made. So in the past, we've been using this function called predict. Oh, there we are. We've been using this function called predict. But I want you to be aware that in many sklearn models, there's actually a function, and you can check for your model and see if it's there, but there's typically a function called predict proba. So predict will just give you the 0, 1 binary values. It automatically looks at the probability, decides the threshold is 0.5, and then makes that prediction. But you can actually look at the probabilities underneath, and they're going to give you an array that has 2 values for each row. for each observation. And the first value is the probability that the prediction is 0, and the second value is the probability that the prediction is 1. And you're like 9.92, that's not a probability. Well, it's this e to the 0, 1, so it has it in scientific notation here. So just know that this is actually like quite small number here. So this is like 9.9, and this one's like 0.0072 or something like that. And I should format that so it's a little easier to see, so I apologize. But I want to note here that each of these probabilities will sum to 1. When you add these two probabilities together, no matter what model it is, no matter what algorithm, for every single observation, the two of these together will equal 1. So you don't actually need both. You usually only need one. You can infer the other. And that's, by the way, if you take theory of probability, that's a foundational assumption. All of our probabilities will sum to 1. The probability of all the events occurring added together is 1. And so the probability of the first one and the probability of the second one. So if we want to store these probabilities, we can store them and then grab the one of the first set of outcomes, the positive outcomes only, and we can plot all of these thresholds. So remember I said you can have a threshold. Well, what if we did the threshold at 0.1, and then we did it at 0.2? What's our model performance? Then we did it at 0.3. What's our model performance? Then we did it at 0.4. What's our model performance? So if we did that a bunch of times, a lot of people like to produce this graph that has the false positive rate and the true positive rate, and this is the model performance at every single threshold. So how is the model performing at if we set the decision boundary to 0.1 and then we set it to 0.2? A model that was perfect would look like it would come all the way up here to 1 and then all the way over here. So this is actually like a pretty good model. And people actually use the area under this curve sometimes as a metric. So if you have more area under the curve, that means this came up higher and over here, and that's probably a better model. And if you have less area under the curve, if it's going like this, that's probably a poor model. But know that this actually isn't a representation of how the model will predict. It's how the model will predict at different thresholds. So when you actually implement the model, you're only choosing one of these thresholds, exactly one of these. So one of these true positive, false positive rates will be true because you have to choose one threshold for that model to predict at. Usually 0.5 by default. Okay, so that's just useful to know. I'm not gonna ask you to do anything with that, but it's quite handy to know that models are actually probabilities under the hood, and then they're transformed into the outputs that we want them to be. If I was going to ask you to take anything away from today, it would probably be these modeling methodology steps. So first, of course, read in your data, and but you're then going to progress into splitting your data before performing your EDA, your data prep, your model types, your hyperparameters. So the point I want to make is you'll see online, or a lot of other tutorials, they'll pull in their data and they'll just jump straight into EDA. And that's one way to do it. EDA, by the way, is exploratory data analysis. Sorry, I think I spelled it out here. They'll jump straight into building plots, and I would ascribe to the methodology that if there's enough data, if your data is big enough, do the EDA after train test split and only do it on your training data set. So like truly try to preserve the integrity of your validation and test set, and try not to trick yourself into thinking, oh, I didn't know that this was going to happen, but really you kind of found that out in EDA. So try to prevent yourself from cheating as much as possible. So the purpose of the validation set, I think one keynote here is the whole point of the validation set, we said this is to compare across model classes. It's for hyperparameter selection and cross-validation. It's what it should be used on. So if somebody asks you in an interview, what's the purpose of a validation set? What's the purpose of a test set? Validation set is to compare performance across candidate models. The purpose of a test set is to estimate how well your model will generalize to unseen data or generalize to the real world. So first train, test, split, then go into EDA, then data prep, can't type, data prep, feature engineering, feature selection, then your model tuning, hyperparameter selection with cross-validation, then your challenger model on the validation set, then your final model selection, one-time evaluation on the test set, and then deploy your model. I'll probably go into like even more detail here because I realized I didn't put add all your data back together and retrain it here, but I'll add that. But if you want even more kind of like granular detail, a few more steps laid out in there. I think we're going to skip breakout today, but what I have here is, maybe we'll come back to this at the very end if there's time, but what I have here is a breast cancer classification. This is a really, I told you I'd give you resources here. This is a really popular website if you're looking for data sets. So we talked about Kaggle, a lot of great stuff out there. A lot of the Kaggle data sets are actually sourced from here. So you can see the irises one on here. So you'll see a lot of data sets repeat multiple places, but there's a ton of data sets on here. It's a very well-known repository for data. And so this is a breast cancer data set that's been around for some time. It's actually been around so long I had to update my code to run this because it looks like they changed some of the stuff in this. But if we import these packages, and then they have this neat little like function that just gets you the data, which is nice. You might have to install this, pip install this to do that, but it's pretty cool. And then we do our train, test, split, and we set up our pipeline, all the stuff that we've learned here. In this case, we're just doing one transformer because all of these columns are numerical. They're all scalar columns, so we don't need to do any categorical column transformations. And what I'm trying to do here is set up a model evaluation of how it performs at all of these different max depths for a gradient boosted tree, which we'll talk about trees next time. But basically, I have this model parameter, and I want to see how the model performs when the parameter is 1, when it's 10, when it's 50, when it's 500, because I want to show you what overfitting looks like. So I set all this up, and then the breakout was going to be to plot that performance against the model parameter, but maybe I'll just do that and then send that to you guys afterwards. And then compare evaluation on the test set here. So moving right along to, let me make sure I covered everything. Yep, we're gonna move right along to grid search and cross-validation. See if we can't wrap up early today, we'll see. So grid search and cross-validation. So we're gonna talk about k-fold cross-validation. We're gonna talk about some resampling methods. Actually, I don't think I have big O notation in here. Well, maybe I'll send out a blurb on that afterwards if you guys are curious. Okay. So k-fold cross-validation. Again, you'll notice that in machine learning, we use the word k a lot when we want to represent like n. And that's going to be a parameter into a model. So k means clustering, where you choose the number of clusters you want to have, k nearest neighbors, k-fold cross-validation. So you'll see that a lot. So if we have what k-fold cross-validation is it allows us to split our training data into different segments so that we can select hyperparameters. So we wanted to tell how well our model is going to fit. We can split the data into training and test our model on the training set and evaluate the test set. But if you evaluate the model once and you're not sure if the result was good luck or was it by chance, so when we talked about that bias variance trade-off, how do you know that it's going to perform well on other data sets, not just the one test data set that you compared it to? So a really common technique, and sometimes this is called a subset sampling technique. It really just depends on the text that you're reading. I really think it's its own methodology and things, so I don't have it labeled as that here. But you pass a single parameter called K, and it's sometimes called CV, and that refers to the number of groups that the data is split into. So if we're doing, in this case, let me just jump down to this picture. We're splitting into 5 groups. So this would be K is equal to 5. We want to split the data. We want to train a model over the data 5 different times. And so we're splitting into 5 different, what are called folds. And so as such, this procedure is called K-fold cross validation, and where a specific value of K is being chose. Typically, people go in sets of like 3, 5, 7, 10. I've never been able to use 10 because you're going to need a lot of data in order to use 10. Otherwise, each of your folds, your splits that you train through are going to be really, really small. 3 is sometimes used. If you're doing anything less than 3, just don't do cross-training, K-fold cross-validation. Just train with all the data set if you can't afford to split into 3 different data sets for your data. So let's just walk through the algorithm here. So we have all of our data here at the top. Got all our rows. We're going to split that into our training data and our test data, and know that that's, test data, test validation data, whatever. Set all that aside. The test and the validation, set it aside. Okay, so now we have just our training data. So to just our training data, we're going to split that data into 5 different segments. So we're going to say 1/5 of the data is called fold 1. 1/5 of the data is called fold 2. 1/5 of the data is here, 1/5 of the data is here, and 1/5 of the data is here. So if we have 100 rows of data, 20 are here, 20 are here, 20 are here, 20 are here, and 20 are here. So 20 observations in each fold. Now, when we go into split 1, what's going to happen is we're going to train the model using 4 of these folds, and we're going to evaluate on this last little piece. So we're going to set aside this first segment, this first fold of data, and we're going to train on these 4 and evaluate how well the model did. Okay, so now we're going to move to the next iteration. We're going to do the same thing, and we're going to train on these ones in green this time, and now we're going to evaluate on the second fold. And now we're going to do the same thing over and over again. Train on 4, 5, 1, and 2. Evaluate on 3. Combine 5, 3, 2, and 1. Train on that. And test your performance on 4. Combine 1, 2, 3, 4, and 5. And then use 5 to actually assess how did your model perform, to create your model metric. That's what you would say is like, what's my accuracy on 5, for example? What's my accuracy on 4 for this run? So that's a 5-fold cross-validation. And so then at the end of this, actually, let me think. Let me pause here, think if I'm missing anything. Yes, okay. And all of your model parameters are the same here. So if our, I'm trying to think of k nearest neighbors. If we're training k nearest neighbors is equal to 3 for all of these runs, for all 5 of these runs. But maybe the performance is 0.8 here, and maybe it's 0.7 here, and maybe it's 0.9 here, because the performance might be different because, see, we're giving it different training data, different pieces of examples, And then we're evaluating on unseen data. The blue pieces are unseen, but it's different. The unseen data is different for each run. Okay, is this clear as mud?
Yeah, it's very muddy.
It's like, yeah.
Okay,
It's very muddy.
let me think.
So,
I might whiteboard this. I don't think this is going to make it any, so here's the algorithm. I don't think this is going to make it any clearer. I'll go through these last two pictures and then I'm going to try to whiteboard this because this is very important. This is quite important to machine learning. So we're going to divide the data set into K parts. So in here, these are all different segments of the data set. We're breaking it all apart. And we're going to use K-1 parts and 1 for testing. And then we're going to repeat this process K times, rotating the test set. So this test set's going to be here, and then it's going to be here, and then it's going to be here, and then it's going to be here. And then we're going to determine the expected performance metric. Okay, so one last visual just to make a point about how the performance metric is actually calculated, and then I'll break this down. So if we think about K-fold cross-validation is basically just our train test split, but we're applying it a bunch of times just on our training set so that we can choose our hyperparameters that we're looking for, which I'll describe what that means in a bit. But we have this entire data set. So this is the same data set here. Each row is the same, each iteration is the same data set. And we're breaking this data set down into 5 pieces, where this is 20 rows, this is 20 rows, this is 20 rows, this is 20 rows, and this is 20 rows. And when we train the model the first time, we're going to train it just on these gray blocks. So on these 80 data points. And we're going to evaluate on this blue section here, what's calling the validation fold. These 20, we're going to evaluate on these 20. And from that, we're going to calculate a performance metric. And we're going to do that 5 times total. But we're going to move the validation set. So if the validation set were rows 1 through 20 in our Excel sheet, they're now rows 21 through 40. And then they're rows 41 through 60. And then they're rows 61 through 80. And then they're rows 81 through 100. I probably messed up my counting, 101. So you can see that when we train the second time, this time we trained on all these data elements, but when we train the second model, we're going to train on the first 20, not the second 20. We're going to leave those out. We're going to train on the third 20, the fourth 20, and the fifth 20. So we're going to add all those gray boxes together, train on that, and then evaluate on this data set. And then we're just going to move that across our data set like a little slider. And we're going to calculate our performance on each of these blue sets. And then we're going to average that. So 1/5 because there's 5 blue boxes. And then the sum of all those performances and the average of them. So the average performance across K folds. Is that slightly clearer? Okay. Well, we're going to whiteboard this. Last thing to note. Oh, this is a great picture. I do like this, but it's hard to capture everything. At the end of this, so we've trained all this model. We did cross-validation. Great. We found which parameters had the best performance. When you're done, when you're actually calling predict on your model, what it's done under the hood without you needing to do it, which is really nice, is it's added all this data back together, and then it just trained over the entire data set. So this is an estimation of your performance, but your model has actually been trained with all of the data. So there's no holdout data within, like built in. So your model is not like only restricted to 80 elements. You know, it's got all 100 elements in there. This is just how we estimate the performance. Okay, so let's whiteboard this. Let's see if we can, this is quite important. Let me see. Does this work? Okay, let's just do full screen. Okay. Push this chair in here. Let's see what's whiteboard over here. Oh my. I lost this. All right, works. Okay. So we have, let's see, what should we be predicting? Maybe apples, bananas, pears seems good. So I'll just do 5. We have a data set of 5. Oh, I'm not going to try to draw a picture of an apple. This is an apple. Just use your imagination. A banana, pear. You know what? I should do something just an apple or not an apple. I'm realizing I should. We're just going to do apple or not an apple, 1s or 0s, just to simplify here. 1, 0, 1, 0, 0. There we go. Okay, so we've got our this is all of our data. And pretend that we already did some we have over here a validation set, and we have over here a test set too. We're just not going to use those, okay? So this is just our training data set. So when we say X-train, that's what we mean. This is our X-train data set. So this is our X-val, and this is our X-test. And actually, this is X and Y, because I've got my labels in here, but that's not important. So when we want to do cross-validation, let's say that we want to understand if we're applying K and N, and we want to understand if K equals 1 is better or K equals 2 is better. And what we could do is we could pass all of our data in here, and we could say, here's data R1, here's our 0, here's our 1, here's our 0, and here's our 0. We could pass that to each of these models. These are 2 different models, a KNN model with K equals 1 and a KNN model with K equals 2. Look at one neighbor, look at 2 neighbors. And we could say, pass in the same data here and train the model and then evaluate on our validation set. So how well did you perform on your validation set? And maybe this one did 0.8. And maybe this one did 0.2. So it did really bad on the validation set. And so we might say, oh, K equals 1 is better. But the question is, was there just something wrong with our validation set? Maybe the validation set, we messed up and it only has 0s in it or something. And so we don't know if our model is going to generalize or if we just got lucky or if it was just random. And so people invented this methodology called cross-validation. I'm a slow, oh my goodness, slow eraser. So they invented this methodology called cross-validation, which is, what if we could kind of simulate train test split, but just on our training set and use it to select that. So if we want to set, and I realize I chose K and N, and I have Ks over here, and then I'm going to choose Ks for cross-fold validation. So I'm going to use CV instead, CV, for the number of folds. So let's say CV equals 5, which don't do this. If you only have 5 elements, don't split it 5 times, but just for this example. So if we have CV equals 5, we're going to split into 5 different folds. And so 1, 0, 1, 0, 0, 0, 0. I'm gonna have to actually come back to k equals 2 here in a second. 0, 1, 0, 0. So we're gonna make 5 copies of the data, okay? And we're going to split this 5 times. So here's, you know, 1 record in each split because we only have 1. So the first time that we train the model, we're going to hide this record. So we're going to say train, but only train on these records. And so we're going to send that to the model. And the model is going to say, okay, I'm just going to make up numbers here, but here I did 0.8. And now we're going to say, okay, do it again. But this time, don't look at this one. We're going to cover it up. It's like you're at the eye doctor and they asked you to cover up one eye. Right? We're going to cover up this record and train on this. Now, how well did you do? Pass it our hidden test set that we kind of set aside. It says, okay, well, on your hidden test set, on this little box here, you know, I did 0.6. And then we're going to do that again, but we're going to shift our slider over. So it just shifts across the data set, and we're going to continue to do that. So each of these are a different run of the model. K equals 1 for all of these, 0.5, 0.8, 0.6. Okay, now we would take all these, we add them up, and we divide by 5. And I don't know what that is off the top of my head, but I don't know, we got 8, 5, 6, somewhere around 0.7 probably, right? So we would average all of our performance across each fold, across each split, and that would be the performance, where we're just hiding a segment of the data. How do we know how much data to hide? Well, C equals 5, and we're going to hide one of the segments, so it's a fifth of the data. If C equals 3, we're going to hide a third of the data. If C equals 7, we're going to hide a seventh of the data. That's kind of typically how it works. You hide one fold out of whatever the number is, so your number minus 1. So that's K equals 1. Now, what if we had K equals 2? So what's the whole point of crowd? Why even do that? Well, the point is that we probably don't know what value for K to use, or we don't know what value. Models have tons of parameters. When we get into trees, you'll see that you can have like a depth to the tree, you can have number of trees, and so when we get to that, you're going to need a way to choose the best parameter. And so this is how you do that. So we would do the same thing. It would look exactly the same here. C equals 5, and we have our 1, 0, 1, 0, 0. Again, we're going to make 5 copies of the data. Doesn't actually make 5 copies, but it's a useful way of thinking about it. And we're going to have our hidden test sets for each run. And we're going to say, okay, train a model with K equals 2. And in this case, maybe it starts to look like it's doing worse. It has 0.3, but then it really turns a corner. And that was just a weird thing that it performed 0.3. And the rest of the time, it's like 0.9. And so somehow we get this metric that's 0.8. So you can see how just the thumb in the air on one validation set, a one-time evaluation, isn't as robust as this, because we have this like generalization across all these different runs of our data, and so it probably is 0.7. Again, you have to make sure you have sufficient data. Like I almost never split 5 times unless I have a lot of data. I usually split 3. So make sure you have sufficient data to do that kind of many folds. But so you can see how this creates like a much more robust metric. And I can say with much stronger certainty that K equals 2 probably really does outperform K equals 1 in the general case most of the time. There's going to be situations where it doesn't, obviously this one and this one. But again, we're looking for probability, right? So when you're thinking about probability, if we have a probability of 0.8, that means 80% of the time it does one thing and 20% of the time it does another thing. And so you could be of that situation where it doesn't outperform it, but most of the time, that's what we're working towards. So that's how it'll help you choose your parameters. Okay. That's about as close as I can get. How are we feeling?
Well, I think my thing is, so like the one that says 0.3, obviously it did worse, and we are looking at it in separate cases each time. I guess if I were to see that, I mean, I know that some of the data is not doing as great, so like, I guess what would I do to make it better? I don't know.
Oh, that's a good question.
Because you
Yeah,
know that's something in your data that could possibly be, I guess, improved.
definitely. And you should do all of that too. You should. I think I have a good example I can show you of exactly what you're talking about. Of a time, somebody on the phone will like it because it's actually a data set that classifies land images. So we can go look at that if you guys want. I'll leave this up. I don't need to erase that. I'll erase that after. Let's look at that. And that's a situation where, to your point, you're going to have to go back into the data and figure out what's wrong with it. It may take me a second to pull it up. 1 second.
Because is that what you would do in like the real, or if you were doing that at work and you saw that, you would have to go back in?
Absolutely. Maybe not. I don't know if you'd see it in cross-validation. But let me show you an example of where you would see it, and let me see if that resonates with you. Let's see. So there's this land cover classification problem where you can try to,
You're not sharing your screen.
oh no. Oh no, I'm not. Thank you. Do we have this one? This one we usually do. Okay, so there's this, how do I make this take up the, we usually do this one, right? Okay. There's this land cover classification problem where you're trying to predict which types of images these are. So they have all these images classified by different types. So we have annual crop, right? And you can come in here and we can look at, this is what the annual crop images look like. And then we have residential. These are what the residential images look like. When you're trying to train a model, this is like a classic problem, you're trying to train a model to detect these different classes that they have laid out. Here's highway, images of highways. So somebody's clearly come in and labeled all of these data sets. So if we try to find this, there we are. So if we try to train a model to predict on that, it might do really poorly. And sorry, you cannot, let me take the classes out of here. Oh, then you're not going to be able to. Okay, just know that this is a poor visualization and that this goes in the same order on the bottom as it does in the top. So it goes annual crop, forest. So this is annual crop, this is forest. Sea Lake is at the end here, so apologize for my, I should have turned those. So you can see that when it's trying to classify this one here, which happens to be residential, you just can't read that, that these are all the situations in which it gets that wrong. So you can see, for residential, here's where it got it correct, 318 of the time. You can see it's really confusing residential with like permanent crop, and it's really confusing it with industrial and highway and vegetation. And I think I even have another confusion here. This one's a little clearer, sorry. This is maybe like a slightly better trained model. So it really highlights the problems even more. So anywhere that you start to see like the colors get light, so this diagonal should all be lit up. That's where we want the diagonal to light up, and we want the predictions to match the true labels along that diagonal. Anytime you see boxes outside of the diagonal light up, that's where you know the model is getting wrong. And the lighter the box, the higher the count, the more incorrect it is. So for residential, you can see the biggest classification mess ups here are highways and industrials. So that's telling us like something about the model, something about like the way it's making its decisions on the images. It's having trouble distinguishing between highways and industrial. So we should probably manipulate our images in some way to help it be better at creating decision boundaries that define highway and industrial. And if we look at like highway here across here, you can see we're having all these different predictions. Like it doesn't even know what to do with a highway. It doesn't even know what a highway is. Like it's so confused. It mostly thinks a highway is a residential, and because of this line up here. And so the other one that you can see that gets confused a lot is this herbaceous vegetation. And so a lot of times it's confusing that with permanent crop, which in my head makes sense. What's the difference between a permanent crop and an herbaceous vegetation? Like those probably do look really similar. And so we have to help the model somehow parse through these things. So I'm hoping that resonated with what you were saying, is then at this, you would look at this and say, like I know the areas I need to focus on and what I don't need to focus on. Like I probably don't need to focus on like this. Well, that's not true. I probably don't need to focus on the sea lake. Like the sea lake's doing pretty good. Like for some reason, sea lakes just don't look like anything else. And I really probably don't need to focus on the forest. Like the forests are doing really well. So you can use this to figure out what about your data do you need to manipulate. And sometimes you need to do things like make fake data. Like that's a real thing. So maybe I don't have enough examples of certain types of data, and I can like make more fake data. I can like take a picture and I can like turn it left and turn it right. And I can take a picture and I can like change the color a little bit, and I can make it fuzzier over here. And I can kind of manipulate the image and make more fake examples for it to perform better. Okay, that was a total side tangent, so I apologize. All right, all of that is k-fold cross-validation. Let's talk about another thing that goes very hand in hand with k-fold cross-validation. So they're different concepts, but they happen together almost every single time, and that is grid search. So you'll see that like even in sklearn, our grid search CV method has a k-fold parameter. So they're tightly coupled. They usually happen at the same time. So a grid search, or otherwise referred to as a hyperparameter search, is a characteristic of a model, and you're trying to determine like what that hyperparameter is. For k nearest neighbors, k is a hyperparameter. Anytime you're trying to like choose this attribute about your model and you don't know which one's the best attribute, that's a hyperparameter. And so for random forest, it would be like number of estimators when we start talking about random forest. And so this hyperparameter, we can do this thing called a grid search, where we have these different parameters. So if we had, I'm struggling because I usually use decision trees in random forest, but we haven't talked about those yet, but I'm just going to use them because k-nearest neighbors, the problem is it only has one parameter. So in this visual, there's two parameters. So if we have a decision tree and just, that's exactly what it sounds like. You can have a depth to a decision tree, and then you can have like a number of trees, and that's what a random forest is maybe you want 2 decision trees, maybe you want 3. So perhaps this first parameter is like how many trees we have. Do we have 0 trees? Do we have 5 trees? Do we have 10 trees? And perhaps the second parameter is like how deep is the tree? Is it 5 deep? Is it 10 deep? Is it 15 deep? Is it 20 deep? And just know that these are parameters of models. And so each of these points is a model. So think how many models are on this. There's a lot. And the combination of like 10 and 5, so the combination of like 10 trees with a depth of 5, that exact model would plot to like right here. And so we can see that, there's a plane to this in this 2-dimensional space. And this is our objective function. I'm so sorry. What are we plotting against here? This is our objective function. How well is our model doing? So in regression, it's typically mean squared error. And we want to minimize mean squared error. So that would be gradient descent. We want to move towards the bottom here. In some other algorithms, maybe you want to maximize it. So maybe it's like accuracy, right? Accuracy, we want really high accuracy. We have gradient ascent. So you can go up or down. Typically people like to think of down, like a ball rolling down a hill. Gradient descent is one that you'll think of a lot. So immediately we can look at this picture and see, oh wow, the best model is definitely down here. So why don't we just pick that model? Well, first of all, this is just 2-dimensional space. And even in 2-dimensional space, that's hundreds of models. And it would take us a very, very long time to train all of those models. And so what we typically do is we actually just initialize a bunch of different parameter combinations and we train them randomly. And so we randomly train a bunch of different combinations here. So we don't usually get such a good picture of the entire space. We have a little bit of a visibility into a small amount of the space. And then it's usually in many more dimensions than 2. So it gets quite complex, actually. But the intent behind the grid search is to either maximize or minimize your objective function. So in here, whatever our metric was, maybe this is accuracy. Our intent was to maximize accuracy. That was the goal of doing the grid search. Find the model that maximized our objective function. Okay. I think one thing I didn't note here about grid search that I think is worth noting, when you do apply grid search, and I think I have an example in here. I do. So we're saying these are the parameters that we want to search over. And in this case, I'm just searching over these max depth for a tree. So it's just one parameter. So it'll train a model first with 1 max depth, then with 5. However, for every additional parameter that you add, so if we say GBT, and down below I have the default values for a gradient boosted classifier. So that means that these are all the potential things that you could change about it. So let's just pick one. Let's pick N estimators. You don't need to know what this means. I just want to make a point here. Which is that if I said N estimators is equal to 100, well, before we had 1, 2, 3, 4, 5, 6, 7, 8 models that would have been trained. The moment I add another parameter to search over here, we instantly have 16. Because the model is going to train over something called the cross product of all of your parameters. So that means the combination of 105, 101, 105, 110, 120. You get the idea. Okay, so let's do a simpler example here, just so I can add 200. So now we have 3 times 2 models. So 3 times 2. So we have 6 models, and that's because it's going to train over 101, 105, 110, and then it's going to train over 201, 205, 210. And if we added another parameter here, let's say we added learning rate. Now, and we said 0.1, well, that's going to be the same. Now, if we added 0.01, we just doubled the number of models that we're going to train over. So now it'll train over 3 times 2 times 2. So now we have 12 models. So you can see it gets really big. Now we have 12 models and we don't even have that many parameters. So a parameter search can actually be really complex because the number of models that you have to, the number of models that it would make you train to get there. Okay. Now let's go back to this example. We have 1, 2, 3, 5, 6, 7, 8 models. Okay, we're training 8 models, 1 with each of these parameter sets. When we do that, we're also passing CV equals 3. So we're not really training 8 models, we're training 3 times 8. So we're training 24 models because it's going to train one of these for each fold. So not super important to know right now, but just when you are training a model and you're using a fairly large data set and then it's taking an obnoxious amount of time, maybe check out your grid here, maybe slim that down. This is where I wanted to talk about big O notation, but I won't. But maybe just try to run your time estimate on just 1 model with 1 fold, then try to up it to 3, see how long that takes, and then you can kind of use that to generalize how long your model is going to take to train. Some of these models can take quite a bit of time if you're putting in a whole bunch of parameters and if your data set's really large. Okay. We're way over time for a break. Let's take a 10-minute break. And then we'll try to get through the rest of this. We'll talk about resampling, class imbalance, and then feature selection and accuracy, precision, and recall. So I'll see you guys back at 8:22. Okay, jumping into class imbalance. This is I know I say this about everything, but again, this is a very important thing in machine learning. I wouldn't say this is like as pervasive as cross-validation, right? You'll see cross-validation everywhere. This is specific to certain problems. Some problems are class imbalance problems. That means that there is great disparity between the representation of the data in the majority class. Look at all the red dots. There's a lot of them. And the representation in the minority class. Look how many blue dots are. There aren't very many of them. And that can be hard for models. I know it's easy for us humans to look at that sometimes and be able to like sort through all that noise. But sometimes machine learning models are really biased by like popularity. They're easily influenced by what's popular, I guess. And so you can think of this majority class as making it hard for the model to make decisions on this minority class. It's probably going to perform poorly on the minority class. So those are specific data science terminology, by the way, minority and majority class. There are a couple of techniques. By the way, your fraud data set that you're going to work with is a very classical example of class imbalance. So fraud, 99% are not fraud, 1% are fraud. That's a very standard example. And you see that kind of across a lot of industries. So what can we do if we have class imbalance? How can we make the model better? Because you can do all the hyperparameter tuning you want. You can do all this stuff, and your model's probably really not going to get that much better because it's struggling with like your base data. So resampling techniques are a way of manipulating your training data set to represent your classes differently. And so there are two main techniques, I guess, that we can start to understand fundamentally, two basic ones. And once we understand these, we can build like much more complex algorithms. There's undersampling, where this is your original data set here. So little tiny fraud example, lots of non-fraud. You can do undersampling, which is basically, I have too many examples of non-fraud. I just want a few examples of non-fraud, and I'm going to make the distributions match. So in this case, they made it 50-50. So see, we just threw away, we deleted a ton of examples of non-fraud. We deleted data because it was probably redundant, honestly. And so another technique is called oversampling. We're going to create a new training set. But in this case, we're going to take our examples of fraud and we're going to make a whole bunch of copies of them. And so we're going to, take that times 10. Be careful. This does violate some assumptions when you're working with very small data sets. Remember, I talked about there were assumptions of linear regression, but we just wave our hands. One is that every sample is independent. This is not the case. But let's assume, we're assuming all big data sets for this class. So in that case, you can just make a bunch of copies of your minority class. So we made 10 different copies here. And now this is a 50-50 representation. So those are two techniques. Oh, I described them here. So random oversampling, and you select these at random. You randomly duplicate examples in the minority class, and undersampling, you randomly delete examples from the majority class. What if we could kind of like combine these? Wouldn't that be cool? There's this algorithm called SMOTE. So you may hear this, and this is probably, or was, I guess, the most popular sampling technique for class imbalance. There's probably much more sophisticated algorithms about now, but basically it's synthetic minority oversampling technique. And so this is an oversampling technique, but you're basically going to create a bunch of fake data. And so we have this original data set here that's all these majority class, but there's too many of them. And then our minority class. What it's doing is it's kind of interpreting some values between these points. So it's sort of intelligently sensing, well, if this is a housing data set and I've got a house here for 150 and a house for 100, maybe I should make another house for 125. It's logical to think that there would be a house in between. So this is like a gross oversimplification of this algorithm. It's really, really common and pretty neat and used a lot. And so this is your resampled data set. You can see now this is what you would use for training. So you would do all of this before training your model. And so this is on your training data set. This is after you've done train test split. You set aside your validation and your test set. You would then apply these resampling. So, oh, I wanted to show you something. Have you guys used ChatGPT? If you haven't, you can, if you need code, you could just ask ChatGPT to make you code. So ChatGPT wrote me this code. I even have, yeah, you can, I encourage you to use ChatGPT to do all of those things. Like that is how it's going to be in the real world. You're not going to get in trouble from me for using AI to write your homework. That's fine. Like the point of this class is to teach you how to apply this in real life. And if this is how you do it, that's how you do it. So that's fine. So anyways, I asked it, hey, can you write me Python code that uses SMOTE to address class imbalance? And it even defined the technique and why SMOTE's cool. And then it even told me that I need to install this, which I did need to install before running this. This is the most common package for resampling techniques, imbalance learn, imblearn, sometimes it's called. Here, imblearn. So it wrote all this code and I tried to run it. You can test it out. My version of it technically won't work on mine because my version of sklearn is out of date and I can't update it right now because some code I'm running that requires that old version. So this is why you should do environment management. I don't have that set up at the moment. So so you can try this. I imagine it runs correctly, which is cool. So anything in this data set and you're like, how do I do that? Like, how do I apply cross-validation? Like, write me Python code that uses cross-validation from sklearn. And it just writes it for you, which is pretty cool. Cool. They use stratified k-fold. Can you show me how to do cross-validation with grid search? Cool. So you can use all this stuff. It's kind of neat. That's all I wanted to say on that. Let's see, we have 30 minutes. What did I have left on here? I may skip our basic review of feature engineering. We talked about that last time, so I'm going to skip that to go straight to feature selection here. So if you remember, I'll just say one thing on this. If you remember, we had all these features about something. So in this example, we're creating a function that takes in some data and tries to predict the price of a car. And some features might be the horsepower or the number of seats or the year, four-wheel drive, or the description of the car. You can imagine how these things might be useful in predicting the price. So maybe more horsepower is more expensive car. But feature engineering is when we take all these values and we convert them to numerical representations. So this is a feature vector. So somehow this has to be put into a numerical representation. So remember, we talked about one-hot encoding, we talked about ordinal encoding, we talked about scaling if these features needed to be scaled. I think there's one more thing I wanted to say in this slide. So when we say feature engineering, in data science, we mean all of these things. So we mean cleaning the raw data, handling missing values. So remember we talked about imputation, how to impute something, impute missing values. Feature engineering includes the domain of like producing numeric features. That's everything that we did before, the one-hot encoding, and it includes combining features to form new features, and it includes keeping only the useful features. So we're going to do feature selection, which by this definition is a part of feature engineering. I think I had one more slide just on recommendations that I thought was minorly useful. These are just different ways you can engineer features. We're going to skip over this. This is review. We did all this. So if you have a data set and you add more features, more columns, you should probably add more data. So if you have a really small data set, just adding more columns is actually going to make your model more overfit. It's not going to help. So just keep that in mind. Visualizing your data is very, very helpful in feature engineering. It can help you kind of figure out what to do. Again, we've talked about this before. Start with a baseline, add complexity, and analyze errors for intuition about missing data, maybe in an advanced machine learning course when we talk about missingness. Okay, so with that 5-second review, let's talk about feature selection. So we have a huge data set, like just a ridiculous number of features, and we need to figure out how do we select what are the most impactful features to the most informative features to our model prediction. So we want very informative feature. Sometimes you just want to reduce computational costs, but other times it really does improve the performance of the model to drop out these noisy features that aren't adding any statistical value. So there's a couple different kind of like algorithms and approaches that you can use to this. And similar to the way that we talked about the resampling, we're just going to talk about like 2 ways, forward and backwards, and then just know that those generalize into many more complex algorithms. But we'll talk about the recursive feature and elimination. I realized this picture is very small. I was going to pull this up on the side, and I didn't get to it. But basically, I'll send this out. There are 3 classes of feature selection. One is like a filter method. So this is everything that you're going to do before you actually get to the modeling. You can think of that correlation. We showed correlation between features. That's a way that you can do feature selection. And then there's embedded methods that are actually embedded into the algorithm itself. And then there's something called wrapper methods, which means you're going to train a model, get an output, and then feed it back into it, and then train a model and get an output and feed it back in. And that's what we're going to talk about today, are these wrapper methods. Again, I'll send this out. It just has the comparison between those 3 different classes. For feature selection, a really common first place to start is feed forward feature selection. You guys already did this basically, or you did a type of this. You guys had a regression model and you had one X feature, and then you added another X feature, and then you said, how well did it do? And then you added another X feature and you said, how well did it do? And you added another and you said, how well did it do? And so that's really similar to this. So we're in this structure, we train a model using each feature, and then we individually check the performance, and then we give the variable that has the best performance. So imagine if they have this example with all these little balls here. These are our features. So we have no model. Imagine we compared how would the model be if we added X1? How would the model be if we added x2? What about x3? What about x5? What about x4? So we compared the model performance across all these, and we saw that adding x2 made for the strongest model. So, okay, so let's add x2. Next, let's look at the next variable that would be most significant to add. What if we added x5? What if we added x4? What if we added x1? And so you can see this, and then you stop adding variables when there's no more like significant variables to add, no significant improvement in the model's performance for whatever that means. You can set a threshold, like if the model's not moving more than 0.1, then don't add another variable. We repeat this, add one at a time, and the highest improvement. So you can see a lot of flaws with this model. It matters what you start with, and linear combinations are really important. So maybe we never got x3 in here, but if we had added x3, then adding x5 would have been very important. So this is a very simplistic model. The opposite of this is just adding all the features all at once and then taking one out one at a time. So remove the least significant variable and then continue to do that until you run out of variables or you meet a stopping criteria in terms of performance. And so you can do it either way. There's probably more popular technique called recursive feature elimination, which you're going to select features recursively, considering smaller and smaller sets of features. So you're going to train a machine learning model, and then you're going to obtain this feature importance and then remove the least important features and then retrain the model. So you can see that there's a big retraining model piece in here. So here's an example, I think straight from the scalar example of a recursive feature ranking, or I'm sorry, recursive feature elimination. So if we make some fake data here, we're loading the iris data set, the one you're very familiar with here. Iris data set doesn't have very many features, so it probably doesn't make sense strongly for this, but you get the idea. So we're splitting into xtrain, xtest, and ytrain, ytest, and we're training this random forest classifiers, and we only want it to select one feature. So we're telling it, I just want the most important feature. You know, normally you'd make this 5 or 10 or 20 or something. So we're calling this RFE, this recursive feature elimination. We're passing our model, and we're passing the number of features to select. So we're saying just one. And then we're fitting this. Again, this is its own type of model. And then we get this feature ranking. And then we can figure out what is the most important feature, I guess, in terms of our model. And so this would allow you to select a set of features. It would automatically select a set of features for you to feed into your model. Let's see, I think. Okay, I kind of went through that fast because I did want to get to this, like just touch on this classification metrics, and then this is it for today. So I skipped all the breakout exercises, but I guess we needed the full time. So intro to modeling metrics classification. So we talked about like R squared and mean squared error. We talked about for regression, how do we calculate like the distance between our prediction and the actual value? We subtract those. We square those, take the sum over all of them. But how does that work for classification? So, you know, we had these images. How does that work if I'm saying this is a 4? What if I said it's a 1 instead of saying it's a 4? How incorrect is that? How far off am I? How do I evaluate a classification model? And for simplicity, in what I've said so far, for most of the things that we've talked about, I've said accuracy because I think that resonates with a lot of people. But accuracy, we want to be really, really careful here. Accuracy is an actual metric. So whenever you're talking about the performance of your model, I would highly recommend that you use the term performance, that you never say my model was this accurate unless you truly are using the metric accuracy, unless you're really measuring accuracy. But in terms of fraud, for example, accuracy may not make sense. So what is accuracy, like quantitatively? Like, what is the formula for it? We're going to talk about what these are, but it's all the true positives plus the true negatives, all divided by the true positives, false negatives, and the true negatives. So how many did you classify correctly? What are all your true positives and your true negatives? Truly a positive prediction and truly a negative prediction versus all of the data. So that's what accuracy is, the proportion of true results among the total number of classes examined. It's a really good metric because it resonates with people. So if you talk with stakeholders, like they know what accuracy is, and so it speaks to them. But we have to be careful because if I trained a class imbalance model, remember we've said class imbalance, fraud, 99% negative, nobody committed fraud, 1% fraud. I trained a class imbalance model, and all my model did was predict 0 for everything. That's what I decided my baseline was going to be. I was going to predict 0 for every class. If I chose accuracy as my metric, my fraud model would have 99% accuracy. And you can see that that's really a misleading metric because never in the world would I ever actually detect any fraud at all. So it's actually quite a useless model in terms of fraud detection, but it has a really high accuracy. So accuracy isn't always a good metric to use, especially with class imbalance. That's the one thing I want you to take away. Do not use accuracy with class imbalance. We need a different performance metric. So I think we've been using confusion matrices in this class, but let's talk about what they actually are. But before we talk about that, we need to understand these different categories. So we have true negatives, false positives, false negatives, and false positives, and they're confusing and can easily be mixed up. But a true negative is when you predicted the value was negative and it actually was negative. So we predicted apple, or we predicted not an apple, and it was actually not an apple, it was a horse. A false positive is when you predicted positive, but it was actually negative. So we predicted apple, but it was actually a horse. And a false negative is when you predicted negative, but it was actually a positive. So in terms of our fraud example, we predicted it wasn't fraud, but it was actually fraud. And then our true positive. So that's when you predict something was positive and it's actually positive. So those are the ones we got correct. We predicted that it was fraud and it was actually fraud. When you see these labels, they'll probably be in this dimension of a matrix. So was your prediction 0? Was it actually 0? That's a true negative. Was your prediction 0? Was it actually 1? That's a false negative. So you can kind of read it in this way. Typically there will be, you just have to know this is true positive and this is true negative, what those definitions are, but there will be numbers in these boxes that represent what proportion of your data set falls into these classes. Let's talk about precision. Precision is a very important metric. And it says of all of our positive predictions, how many were actually correct? So it's the true positives over the true positives plus the false positives. So it's the true positives, over the true positives plus the false positives. So it's just this section of the diagram. So when we predicted an example of, if you're trying to orient this in your mind, what's a precision? When we predicted someone had cancer, how many times did they actually have cancer? We predicted 10 people have cancer, but 9 of those people had cancer. We don't care for a second about the people we predicted that didn't have cancer. We're going to get there. But just for the people we predicted that did have cancer, how many did have cancer? So it's a good metric when we want to be really certain how precise our our prediction is. So if we're building a system to predict if we should decrease the credit limit on a particular account, we want to be very sure of our precision, or it may result in customer dissatisfaction. So recall is another side of this coin, which it's the true positives over the true positives plus the false negatives. So it's the true positives over the true positives plus the false negatives. So now it's this dimension of the matrix. And a way of thinking about it is, of all the positive values that exist, how many did we correctly identify? So in the cancer example, this would be not just of the people we predicted had cancer, but of everyone who actually did have cancer. So that includes the people that we said didn't have cancer. How many did we correctly identify? So the question we're getting to here is, were there some people who had cancer that we told them they didn't have cancer? So that's really important for the medical field, right? So they really care about recall. Sometimes they might care a little less about telling you had cancer when you actually didn't. Like it's better news to probably be told you did and then later actually you don't, than it is to be told you don't and then they never find out until much later that you actually did. So recall is a valid choice for a metric when we want to capture as many positives as possible. For example, if we're building a system to predict cancer, we want to capture if the disease, even if it wasn't true. So you can get all these like really complicated like summary metrics. So you might also hear sensitivity and specificity. That just sums along these axes here. You can also hear these called type 1 error and type 2 error. I don't know, that's confusing. I just prefer to use false negative, false positive. I think it's very indicative of what it represents, but you might hear type 2 or type 1. That's what those represent here. So if we sum this way, we get precision. If we sum this way, we get that negative predictive value, I suppose. This is flipped from the matrix that we had up above. And then accuracy is everything. So accuracy is kind of that whole universe of all of those. Okay, so typically like precision and recall, accuracy is not a good metric for class imbalance, but we do care about the precision for fraud, but we also care about the recall. So we can't use accuracy, but we want to use precision and we want to use recall. In that case, we use something called the F1 score. So the F1 score is the harmonic mean between precision and recall. People in practice almost never use actual precision and actual recall. They all use the F1 score or some permutation of it. So this is a very, very important metric. If you're going to use one score for your models, I use the F1 score for many, many things. You can also look at the accuracy, but the F1 score is going to give you a better representation on how your model is scoring. So we won't go into the formula, but just basically it's 1 over precision plus 1 over recall, which people usually simplify to this format, which is 2 times precision times recall over precision plus recall. So same formula, just rearrange the numbers to make it look like this. And it balances, it like combines those 2 metrics and makes them sum to 1. So the combination of this is a value from 0 to 1, just like accuracy. You can have a precision, or I'm sorry, an F1 score of 0.8, for example. So this is harmonic mean between precision and recall. The reason why this metric is important is because it can be generalized and parameterized. So remember that I said earlier in the course, I said, oh, I have a use case and they cared more about recall than they did about precision because we were sending these letter notifications. And so they wanted to make sure that they heard about all of them, even if they didn't need to hear about some of them. So that would be adding more weight to the recall metric. And so if you decrease this beta value, so this can be parameterized. Instead of having the value 2 here, in the case, well, actually it's a value 1, but we can parameterize this here with this beta squared. So you don't need to know all of this, but just know that we can change this beta value from 1 in our formula. It's 1 because it's an F1 score, so it's beta equals 1. So that's why it's 2 up above, because 1 plus 1 squared is 1, 1 plus 1 is 2, and that's where we get this. We get the 2 here. So that's how you get the 2 in the F1 score. And then 1 times precision is still precision. So that's why it looks like precision over recall here. But if we change this beta to a 2, that changes the way this metric assesses things. And the way that it would change it is if we change the beta to a 2, it would treat precision as more important than recall. And it says, use that when there is more emphasis on reducing the false negatives. So you want to be more sensitive to false negatives. You want to penalize false negatives more heavily, you're going to use 2. In the case where there is more emphasis on reducing false positives, you want to penalize false positives more heavily, you would use 0.5. So if you go above 1, it weights precision, and if you go below 1, it weights recall. And if you use 1, it's perfectly balanced. It's the harmonic mean between precision and recall. Okay. I think that is all we have for today. We'll dive more into these in the next course, but I just thought those might be useful as you're training your model so you can use something beyond just accuracy, but we won't touch on metrics much more in this course today. All right. Any questions? Wonderful. Thank you, guys. We'll see you Wednesday.
Thanks, Emily.
All right.
Thank you.
Bye.